Hello everyone, and thank you for being here today. I'm excited to introduce our presentation on hydrogen. On this first slide, you see the word hydrogen, the central focus of our discussion. We'll explore what hydrogen is, its significance, and how it plays a role in our future energy landscape. Over the next few slides, we'll cover its properties, applications, and potential. So let's get started and dive into the fascinating world of hydrogen. Let's take a closer look at the different types of hydrides. First, we have metallic or non-stoichiometric, also known as interstitial hydrides. These are typically formed with metals and often have variable compositions, which means they don't follow a fixed ratio of hydrogen to metal. This variability allows for interesting electrical and physical properties. Next, we have ionic or saline hydrides. These are formed when hydrogen acts as an anion, combining with metal cations to create salts. They're usually solid, crystalline, and highly reactive, especially with water. Moving on, the uses of dihydrogen are quite broad. It's fundamental in various industrial processes, energy production, and even in hydrogen fuel cells. Understanding dihydrogen's properties helps us harness its potential effectively. Now, let's consider the isotopes of hydrogen. Besides the most common isotope, protium, there are deuterium and tritium. These isotopes have different nuclear properties, which are important in fields like nuclear chemistry and fusion research. In terms of chemical bonding, we also encounter covalent or molecular hydrides. These form when hydrogen shares electrons with other nonmetals, creating molecules like methane or water. These compounds are essential in many chemical reactions and biological systems. Hydrides as a whole are a broad class of compounds that contain hydrogen. They can be categorized based on their bonding type, structure, and properties, which makes them fascinating from both a chemical and application perspective. Lastly, understanding the position of hydrogen in the periodic table is fundamental. Hydrogen sits at the top, with unique properties that set it apart from other elements. Its position influences how it interacts and bonds with other elements, shaping its diverse roles across chemistry and industry. This overview ties all these points together, highlighting the versatility and importance of hydrogen and its compounds in science and technology. Let's talk about the position of hydrogen in the periodic table. Hydrogen is actually the very first element, sitting at the very top. It's quite unique because, although it's placed in group 1 like the alkali metals, it doesn't quite behave the same way. For instance, alkali metals tend to lose one electron to form unipositive ions, but hydrogen can also gain an electron and form uninegative ions, similar to halogens. This duality makes hydrogen quite fascinating. Hydrogen forms a variety of compounds such as oxides, halides, and sulfides. But unlike the metals in group 1, hydrogen has a very high ionization enthalpy, meaning it doesn't lose electrons easily. Plus, under normal conditions, it doesn't exhibit metallic characteristics at all. On the other hand, just like halogens, hydrogen forms diatomic molecules. Think of H2, and it also combines with other elements to create hydrides and many covalent compounds. However, when we compare reactivity, hydrogen is much less reactive than halogens, which tend to be highly reactive. So overall, hydrogen's position is quite unique because it shares properties with different groups, but it also has its own distinct behavior. This is what makes understanding its placement so important in grasping the bigger picture of the periodic table. Since isotopes have the same electronic configuration, they exhibit almost identical chemical properties. The main difference between them lies in their reaction rates, which are primarily influenced by their bond dissociation enthalpies. Let's focus on hydrogen, which has 3 isotopes: protium, deuterium, and tritium. Protium, or hydrogen 1, has no neutrons in its nucleus. Deuterium, also called heavy hydrogen, has 1 neutron, and tritium has 2 neutrons. The key difference among these isotopes is the number of neutrons present. Only tritium is radioactive, and it emits low-energy beta particles as it decays. Understanding these differences helps us grasp how isotopic variations can affect chemical behavior and physical properties, especially in applications like nuclear energy and scientific research. Dihydrogen, or simply hydrogen, is actually the most abundant element in the universe. In fact, it makes up about 70% of the total mass of the universe. That's a huge part, and it plays a key role in many cosmic phenomena. When we look at the solar atmosphere, hydrogen is the principal element there as well, influencing the behavior of the sun and other stars. If we move closer to home, the giant planets like Jupiter and Saturn are mostly made of hydrogen. This light gas gives these planets their massive sizes and distinctive characteristics. But interestingly, on Earth, hydrogen is much less abundant in our atmosphere, only about 0.15% by mass. That's because hydrogen is so light that it tends to escape Earth's gravity into space over time. However, hydrogen's importance isn't limited to just the atmosphere. When it's combined with other elements, it becomes a fundamental part of our planet's crust and oceans. In fact, hydrogen in combined form makes up roughly 15.4% of the Earth's crust. It's also a major component of water, which is essential for all life. Beyond water, hydrogen is found in a variety of biological and chemical compounds. It's part of plant and animal tissues, within carbohydrates and proteins, and forms hydrides and hydrocarbons. So basically, it's everywhere in the molecules that make up living organisms and many natural substances. So, in summary, hydrogen's occurrence spans from the vast cosmos to our own planet's crust and living organisms. Its unique properties and widespread presence make it a key element to understand in the context of chemistry and the universe as a whole. Now, this slide shows us another way to prepare zinc compounds, specifically sodium zincate, by reacting zinc with aqueous alkali, such as sodium hydroxide. When zinc reacts with two equivalents of NaOH, it forms sodium zincate, which is represented here as Na2ZnO2, along with hydrogen gas being released. This reaction is quite important because it demonstrates how zinc can react with alkali solutions under certain conditions. Next, we see the more common laboratory method for preparing dihydrogen, which involves reacting granulated zinc with dilute hydrochloric acid. In this case, zinc reacts with hydrogen ions from the acid, producing zinc ions and releasing hydrogen gas. This process is fundamental in the lab because it's a straightforward way to generate dihydrogen gas safely for various experiments. Overall, these reactions highlight the versatility of zinc when it reacts with different substances, alkali or acid, and how we can harness these reactions to produce useful compounds like sodium zincate or dihydrogen gas. Let's talk about how dihydrogen, or hydrogen gas, is obtained. It is primarily produced as a byproduct during the manufacture of sodium hydroxide and chlorine through the electrolysis of brine solution. During this electrolysis process, specific reactions occur at the electrodes that lead to the formation of hydrogen gas. Additionally, high-purity hydrogen, over 99.95%, can be obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. This method ensures the hydrogen is very pure, suitable for sensitive applications. Another important method involves reacting steam with hydrocarbons or coke at high temperatures in the presence of a catalyst, which produces a mixture called water gas or synthesis gas, often shortened to syngas. This mixture contains carbon monoxide and hydrogen, and it's very versatile because it's used to synthesize methanol and various hydrocarbons. Nowadays, we also produce syngas from more unconventional sources like sewage, sawdust, scrap wood, and newspapers. The process of converting coal into syngas is known as coal gasification. To increase hydrogen yield, the carbon monoxide in syngas is reacted with steam in the presence of an iron chromate catalyst, a process called the water gas shift reaction. This also helps in removing carbon dioxide by scrubbing with sodium arsenite solution. The overall chemical reaction for producing hydrogen through electrolysis of brine can be summarized as sodium and chloride ions reacting with water to produce chlorine gas, hydrogen gas, and hydroxide ions. At the cathode, water molecules gain electrons to produce hydrogen gas and hydroxide ions, while at the anode, chloride ions lose electrons to form chlorine gas. Finally, another common method for producing hydrogen is through the electrolysis of acidified water using platinum electrodes, which is very efficient and widely used in industry. The chemical behavior of dihydrogen, and indeed any molecule, is largely influenced by its bond dissociation enthalpy. This is a key concept because it tells us how much energy is needed to break a bond. Specifically, for dihydrogen, the H bond dissociation enthalpy is actually the highest for a single bond between two atoms of any element. That means this bond is particularly strong and requires a lot of energy to break. Moving on to its chemical properties, dihydrogen is a colorless, odorless, and tasteless gas, which makes it quite elusive to our senses. It is also highly combustible, so it can easily ignite in the presence of a spark or flame. Because it's lighter than air, it tends to rise and disperse quickly when released. Interestingly, it is insoluble in water, meaning it doesn't dissolve easily, which is important in understanding how it behaves in different environments. Now, considering its physical properties, these characteristics are crucial for practical applications and safety considerations. Overall, understanding these properties helps us grasp how dihydrogen interacts with its surroundings and why it plays such a vital role in various chemical processes. Let's take a closer look at how hydrogen participates in bonding. When hydrogen shares electrons, it can form a single covalent bond with other elements. This sharing allows both atoms to achieve more stable electronic configurations. Now, hydrogen's atomic form is interesting because its orbital is incomplete with just a one electronic configuration. In some situations, hydrogen can gain an electron to become H-, which is called a hydride ion. Conversely, it can lose its only electron to become H+, a proton. These processes are often observed when hydrogen is produced at high temperatures, such as in an electric arc or under ultraviolet radiation. Because hydrogen's orbital is only half filled, it's very reactive and can combine with nearly all elements. This makes hydrogen incredibly versatile in chemical reactions. So, the question arises, can we produce atomic hydrogen? The answer is yes, and these high-energy conditions are key to generating atomic hydrogen, which is essential in various industrial and research applications. Let's explore some important reactions involving dihydrogen. First, hydroformylation of olefins. This process produces aldehydes, which can then be reduced further to form alcohols. It's a key step in synthesizing various alcohol-based products. Next, we have the hydrogenation of vegetable oils. When we use nickel as a catalyst, we convert unsaturated oils into solid fats like margarine and Vanaspati ghee, making them suitable for cooking and baking. Hydrogen reacts readily with many organic compounds in the presence of catalysts to produce hydrogenated products that are commercially valuable. For example, it reduces metal ions in aqueous solutions and metal oxides, especially those less active than iron, turning them into their metallic forms. It also reacts with many metals at high temperatures to form metal hydrides, which are important in various applications. When hydrogen reacts with dinitrogen, it forms ammonia, a crucial process in the Haber process for fertilizer production. Hydrogen also reacts with dioxygen to produce water, and this reaction is highly exothermic, releasing a lot of energy. Think of it as a powerful combustion process. In addition, hydrogen reacts with halogens like chlorine or bromine to form hydrogen halides, which are vital in many chemical syntheses. Interestingly, the reaction with fluorine can occur even in darkness, while iodine reactions often require a catalyst. Finally, understanding the chemistry of dihydrogen includes considering whether we can produce atomic hydrogen. This is a fundamental question because atomic hydrogen is highly reactive and useful in various chemical processes. Dihydrogen, or H2, is widely used in the manufacture of metal hydrides, which are important for hydrogen storage and other applications. It also plays a key role in producing Vanaspati fat through hydrogenation, where polyunsaturated vegetable oils like soybean and cottonseed oil are converted into solid fats. In metallurgical processes, dihydrogen is essential for reducing heavy metal oxides to their metallic form, enabling metal extraction. Atomic hydrogen and oxyhydrogen torches are used for cutting and welding metals. Atomic hydrogen, produced by dissociating dihydrogen with an electric arc, recombines on the surface to generate extremely high temperatures of around 4,000 Kelvin, which is very useful in welding. Dihydrogen is also used as a rocket fuel in space research because of its high energy content. Additionally, it's employed in fuel cells to generate electricity. Compared to traditional fossil fuels, hydrogen offers many advantages, such as being pollution-free and providing more energy per unit mass than gasoline or other fuels. Another important application is in the production of hydrogen chloride, a very useful chemical in various industrial processes. It's also utilized in manufacturing bulk organic chemicals, especially methanol, which is a key feedstock in the chemical industry. The largest single use of dihydrogen, however, is in the synthesis of ammonia. This ammonia is then used to produce nitric acid and nitrogenous fertilizers, which are vital for agriculture and food production. So, as you can see, dihydrogen is truly a versatile and crucial element across multiple industries, supporting everything from manufacturing to energy and chemical production. Dihydrogen, which is essentially hydrogen in its molecular form, has some interesting chemistry under certain reaction conditions. When these conditions are just right, dihydrogen can combine with almost all elements. However, there's an important exception to keep in mind: the noble gases. These gases are pretty inert, so they don't typically form compounds with hydrogen. What makes this really fascinating is that these compounds are called hydrides. Hydrides are binary compounds, meaning they consist of just two elements, hydrogen and another element. Understanding hydrides helps us see how versatile hydrogen can be in forming compounds, and it ties into the broader theme of chemical bonding and reactivity that we've been exploring in this presentation. So, essentially, hydrogen's ability to form hydrides with so many elements shows just how fundamental and reactive this element can be in different chemical contexts. Let's take a closer look at how hydrides are categorized. First, we have metallic or non-stoichiometric hydrides. These are typically formed by metals and often have variable compositions, which is why we call them non-stoichiometric. They tend to be conductive and have interesting electrical properties. Next, we have covalent or molecular hydrides. These involve sharing electrons between nonmetals, resulting in molecules like water or methane. They usually have lower melting points and are less conductive. Finally, there are ionic or saline, salt-like hydrides. These are formed when metals react with hydrogen to produce salts, like sodium hydride. They tend to be crystalline and are often used in various chemical reactions as bases or reducing agents. Overall, understanding these classifications helps us grasp the different ways hydrogen can combine with other elements, shaping its chemical behavior and applications across different fields. Saline hydrides, or ionic hydrides, react quite violently with water, and this reaction produces dihydrogen gas, which is essentially hydrogen. Now, when we look at lithium hydride, it's interesting because it's relatively unreactive at moderate temperatures, especially with gases like oxygen or chlorine. This stability makes lithium hydride particularly useful in synthesizing other hydrides that are more reactive or have specific applications. Moving on to the compounds formed with most of the S-block elements, especially those that are highly electropositive, we see some fascinating structures. For example, lighter metal hydrides such as lithium hydride, beryllium hydride, and magnesium hydride. In fact, BH2 and MgH2 are not just simple molecules, they are polymeric, meaning they form extended network structures rather than discrete molecules. Now, regarding their physical properties, ionic hydrides are typically crystalline, which makes them non-volatile and non-conducting in the solid state. But here, the key part, when you melt these ionic hydrides, they conduct electricity. This is because, in the molten state, the ions are free to move, allowing conduction. And if we take this a step further, When we perform electrolysis on their molten forms, dihydrogen gas is liberated at the anode. This confirms the presence of the hydride ion, or H, which is crucial for understanding their ionic nature. So, in summary, ionic or saline hydrides are characterized by their crystalline structure, their reactivity with water, and their behavior in molten states, which all tie into their fundamental ionic character and the way they interact with other substances in chemical processes. Let's explore the behavior of these hydrides. They behave as Lewis bases, meaning they act as electron donors. These are electron-rich hydrides, which typically have a lot of electrons available to share. Now, when we look at the elements in group 14, you'll notice that all of them can form such compounds, like methane, CH4. These compounds are tetrahedral in shape, and because they have a balanced number of electrons, we call them electron-precise. On the flip side, some hydrides act as Lewis acids, meaning they are electron acceptors. These are electron deficient, and their structures tend to have fewer electrons than needed for complete bonding, making them capable of accepting electrons. Molecular hydrides are classified based on the number of electrons and bonds in their Lewis structures. For example, dihydrogen forms molecular compounds with most p-block elements, like methane, ammonia, water, and hydrogen fluoride. These hydrogen compounds, especially with nonmetals, are considered hydrides as well. Since they are covalent, they tend to be volatile, meaning they easily vaporize. Lastly, when we talk about covalent or molecular hydrides, we're referring to compounds where the bonding involves shared electrons, forming molecules rather than ions. Understanding these distinctions helps us grasp their chemical behavior and reactivity within the broader context of hydride chemistry. Recent studies have shown that, with the exception of hydrides of nickel, palladium, cerium, and actinium, most other hydrides in this class have a lattice structure that differs from that of the parent metal. This is quite interesting because it highlights how the absorption of hydrogen can alter the crystal structure of these metals. The property of hydrogen absorption in transition metals is widely utilized in catalytic reduction and hydrogenation reactions, which are essential in synthesizing a large variety of compounds. For example, metals like palladium and platinum are capable of absorbing a very large volume of hydrogen, making them excellent candidates for hydrogen storage media. This ability to store hydrogen has significant potential, not only for storage purposes, but also as a source of energy. Imagine using these metals as fuel sources. It's a promising area for clean energy technology. Hydrides are formed by many elements in the D block and F block of the periodic table. However, it's important to note that metals from groups 7, 8, and 9 generally do not form hydrides. The hydrides that do form are good conductors of heat and electricity, although not quite as efficiently as the metals themselves. Most of these hydrides are non-stoichiometric, meaning they are often deficient in hydrogen compared to what you might expect if they followed strict ratios. For example, some specific hydrides include lanthanum hydride with a composition around La H287, a terbium hydride at about Ib H2, 55, and titanium hydride ranging from TH15 to 1.8. Other examples are zirconium hydride at ZrH1, 31, 75, vanadium hydride at VH056, nickel hydride at NiH0, 60, 7, and palladium hydride at PDH0, 60, 8. One key point to remember is that the law of constant composition does not hold true for these hydrides, because they are almost always non-stoichiometric. This means their exact composition can vary quite a bit, which is important when considering their properties and applications.